Today we have the last problem, problem 5 from the University of Maryland math competition, the part 2 of that competition, where we're given A1, A2, A3, etc. to be a sequence of positive real numbers. And we want to prove or disprove that there exists a real number m depending on the sequence A, but not on n, such that for every positive integer n, um, this expression is true. The sum from I is equal to 1 to n of a sub I over the quantity a sub 1 added with all the terms all the way to a sub I squared is less than m. And again, m depends on the entire sequence, but for a fixed sequence, there's a fixed m that works for every single n. And so looking at this, left side of the expression, there's not an obvious way to really manipulate it into, I guess, a nicer form. And I don't see any way to really bound each term because I guess the really big squared expression is on the bottom, so expanding it wouldn't really help too much. And if you do expand it, you can't really simplify the expression in any way. Um, so the idea is, maybe we want to hope that this sum telescopes in some way. And in particular, I guess one of the most common ways summations like to telescope is if you can write each term in the form, say like a, or because it's a sequence, if you can write each term in such a way like f of n minus f of n minus 1 over f of n f of n times f of n minus 1, then this simplifies exactly to just 1 over f of n minus 1 minus 1 over f of n. So when you sum it over a lot of n, you get that the next term will be 1 over f of n minus 1 over f of n plus 1. And so these cancel. And as you sum, these will all cancel out until you're left with, this first term and then some random term at the end. And so that's what we're sort of hoping to get here. And we see that this should sort of arise naturally because we have this squared term here, right? So that will give the two multiplied terms in the bottom somehow. And so now we just need a way to write the top or the numerator as, a difference of something. And the idea here is to use the sum of the sequence. So if we let S sub n, define S sub n to be the sum from I is equal to 1 to n of a sub I, right? Then we immediately have that each term a sub I over this huge denominator is just, or let me write it as, not use I, use an n here. This would be just S sub n minus S sub n minus 1 all over S sub n squared. And so we're almost into this form now, right? We have the numerator matching S sub n minus S sub n minus 1. It is just the denominator now, right? We have S sub n squared here, but up here we have f of n times f of the previous term. So I guess we want to find a way to relate these terms now. And recall that our a's are positive real numbers. So we can see by the construction of the problem now, we actually have S sub n is greater than S sub n minus 1. And so as a consequence, 1 over s sub n minus 1 is greater than 1 over s sub n. And so we also have that multiplying by 1 over s sub n by both sides. We have that 1 over s sub n minus 1 times 1 over s sub n is greater than 1 over s sub n squared. So we actually have that s sub n minus s sub n minus 1 over s sub n squared is less than s sub n minus s sub n minus 1 over, right, our desired form, s sub n times s sub n minus 1, which is equal to 1 over s sub n minus 1 times 1 over s sub n, or minus, sorry. So now that we have, this relation that each term here is upper bounded by this nicer, expression, we have that the sum from I is equal to 1 to n of a sub I over a sub 1 added all the way to a sub I squared is less than, because each term is upper bounded, the entire sum will also be upper bounded by 1 over s sub n minus 1 minus 1 over s sub n. And I guess when I is equal to 1, s sub n minus 1 isn't really defined, right? As when I is 1, we'd have s sub 0, which isn't really defined. So we actually have to we actually ignore the first term first. Like, let's ignore when I is equal to 1. So when I is equal to 1, we have that it's a sub 1 over a sub 1 squared, which is 1 over a sub 1. So this is less than 1 over a sub 1. Now we just start from I is equal to 2 instead to make our terms defined. From I is equal to 2 to n of a sub I over a sub 1 plus, or added all the way to a sub I squared. Yeah, okay, now this is, or this should be equal. This will be less than 1 over a sub 1 plus the sum from I is equal to 2 to n of 1 over s sub n minus 1 minus 1 over s sub n. And now this indeed telescopes now, right? This will be equal to 1 over a sub n plus 1 over, right, s sub 1 minus 1 over s sub 2, right, plus 1 over s sub 2 minus 1 over s sub 3 plus 1 over s sub 3 minus 1 over s sub 4, dot, 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 all the way to 1 over s sub n minus, say, 2 minus 1 over s sub n minus 1 plus 1 over s sub n minus 1 minus 1 over s sub n. So you see our terms cancel out now, and this way, as we're left with 1 over a sub n plus 1 over s sub 1 minus 1 over s sub n, and s sub 1 is just a sub 1, right, by our definition here. So this is just 2 over a sub n minus 1 over s sub n, which, since this is positive, 1 over s sub n is positive, this is just immediately upper bounded by 2 over a sub n. And so, as a result, we have that our sum here that we're looking at is all bounded by, oh, this should all be, sorry, these should all be a sub 1s. So we have that our sum is directly upper bounded by 2 over a sub 1, which if we set as m follows all of the conditions, right? M depends on the sequence, right? It depends on the first term in particular, but this first term works for all n, right? And so we have that if we set m is equal to 2 over a sub 1, it will be our upper bound for all n, and as a result, m exists, and that completes the proof.